All right, my friends, may I have your attention, please? So, I warned you, rest your hand today because we're going to be cooking today. No, not really. It'd be nice to have some fresh cookies or something, but that's not what I mean by cooking. I'm trying to get as much in because I hear that there's lots of tests and quizzes coming up in the very short week we have tomorrow. Next week, not tomorrow. Over the Monday and Tuesday. You can do most of the Chapter 17 problems by the time we get through today. You won't be able to do all of them, and it's fine. Be glad for the ones that you can do. Make sure that you do them. Please don't wait. This is not a real difficult chapter. Just make sure that you take the time to go through the problems and do them. And I think that you won't mind this too much. It's an interesting one because, yes, there's math, but it's not as math-rich as some of the other topics that we've done, like the gas laws chapters. Every problem was math involved. Even in Chapter 6, the thermochem, you had to just do tons of math. This one, though, is a little bit more conceptual, and it really is important to understand what's underneath. Even for the math problems, what's going on with the math. And then there's some that don't involve any at all. It's just predict the sign on delta S for this reaction or that kind of thing. So it takes thinking, but it's not real difficult. But you have to take the time to make sure that you do the exercises and be ready for it. All right. So today, this is where we landed yesterday. And I remember I gave you just a few topics yesterday. Talked about the second law of thermodynamics, the third law of thermodynamics, this one. And then we quit there so you can work on your lab. The next thing that we have, so that kind of finishes off entropy. We talked for a couple of days about what entropy is. Really two different approaches to understanding entropy. There is Boltzmann's theory about positional probability, but then just a normal chemistry understanding of entropy is how much disorder is there. All right, so that takes us to another topic in Chapter 17, and that would be from this guy right here, Josiah Gibbs, Gibbs free energy. Gibbs was a real pioneer in thermodynamics. He actually won 2 Nobel Prizes in 2 different years. So he was pretty sharp. And it turns out, we found this out last hour, Gibbs was an American. So it took us a while, but we finally got there. An American chemist or he was more of a physicist. But he gave us this relationship, G after Gibbs. We know it as free energy is equal to the enthalpy of a substance minus the temperature times its entropy. So what does free energy mean, and how is that any different from other forms of energy? Well, when you account for both the heat flow and for the change in entropy, you combine them together in this equation. Delta G represents the total amount of energy that a reaction is capable of offering up for work to be done. That even includes some of the entropy change. Just the two of those terms put together gives us the total amount of energy that's available for doing work. This term up here, the G without a delta sign in front of it, doesn't have any physical meaning. So we won't really do any calculations with that. You don't know how much free energy is in a substance. We just know how much it can offer when something changes. So we use that. Now, there are several ways to calculate delta G. This is one of them. We're going to kind of sit on this one for a little while and see what we can get from it. We talked earlier in the chapter about Spontaneous reactions. How do you know if a reaction is going to be spontaneous? Spontaneous, remember, definition is that a reaction will occur without any help. You don't have to heat anything up. You don't have to run electricity through it. It'll just happen. Now I'll come back to this. On the previous slide, we saw this, and this is the equation for Gibbs free energy. I didn't specify which delta S, though, I was referring to. Do I mean the delta S of the system? Do I mean of the surroundings? Or do I even mean the universe? What you need to know is that if it's not specified, it means the system. If it's not specified, it means the system. If I mean delta S of the surroundings, I'm going to put the SURR for surroundings. Or if I mean the universe, I'm going to put UNIV as a subscript on delta S. So if it doesn't say, it just means the system. So I specified in this one. Didn't have to, and you'll see why I did. So we need an expression, something that's going to be able to allow us to connect delta G to whether a reaction is going to be spontaneous or not. So this is a little baby derivation. Don't be afraid of this one. Actually, I'm going to kick out a big derivation that I would have done in this, today, because we're slim on time. I'm just going to keep it out. I'll tell you when we get there. All right. So the first thing that we're going to do with Gibbs free energy equation is we're going to just divide through by T. And dividing through by T is no big deal. In algebra, you can do anything you want to an equation as long as you do it on both sides equally. So we'll just take delta G and divide it by T. And then on the right side, divide everything by T over there. Delta H over T. And now the T disappears in the last term because it's going to cancel out minus delta S of the system. Okay, now does anything in this equation kind of resemble something you saw yesterday? Oh, is what? It's the entropy of the surroundings, right? The delta S of the surroundings is equal to negative delta H over T. Remember talking about that yesterday? That matters. So I know this is a positive term, and delta S of surroundings is negative that term, but it's pretty close. And so what I'm going to, changing slides, I'm not messing with the left side at all. So we know this. Now all we're going to do is take that negative side and move it over to that side. So we'll have delta H over T, which is that. We can substitute it then for negative delta S of the surroundings. Let's do that. So it's going to look like this. Delta G over T equals, this term right here now is negative delta S of the surroundings. And then this term hasn't been affected, minus the delta S of the system. Negative minus a number. That's very annoying. So let's do this. Let's take the negative 1 out from both terms and just make that delta S of the surroundings plus the delta S of the system. Yes? And take that negative 1 term out from both. What do you see inside of the parentheses? The system plus the surroundings equals what? The universe. Right. So inside of this, we have the delta S of the universe. And so that's where I was going next with that. And let's go ahead and replace the inside of the parentheses with the delta S of the universe. So delta G over T equals the what? It's negative 1 times the delta S of the universe. the question is, how does delta G respond to, I'll start over. How does delta G relate to spontaneity? We learned something yesterday. We talked about the second law of thermodynamics. What was the second law of thermodynamics? It said something about a spontaneous process.
Must be an increase in entropy.
If you want to have a spontaneous process, there must be an increase in the entropy of the universe. So, if delta S of the universe is positive, that means the reaction is going to be spontaneous, or the process is going to be spontaneous. Yes? Is that what the second law says? Yes, that's what it says. What is T in this equation? This T over here that we haven't done anything with, what does that represent? Temperature. What unit? Does it have to be in Kelvin? Or could it be in Celsius? Yes, it has to be in Kelvin. Why? Look back up here. Whenever you have a T, not delta T, but just T, it's got to be in Kelvin. If you have delta T, it doesn't matter what you use. But we do have to use T, or Kelvin for the T. So, what's the point of that? If the temperature's in Kelvin, what do you know about its sign? It's always positive. Kelvin doesn't have any negative temperatures. And it's certainly not, it can't be zero either. Because what happens at absolute zero? That's 0 Kelvin. Well, there's no chemistry. We'll just agree with that. There's no chemistry at absolute zero. There's just craziness. Okay? So, if we have a spontaneous process, that means that term is positive. What does that mean about the delta G? Come on. It's got to be negative. If you have a spontaneous process, the delta G will be negative. That's a really important thing. Not just for right now, but for all of chemistry. We're going to revisit this concept almost every chapter from now on. The fact that delta G has to be negative. So here's the wordy way of doing it. Spontaneous means that the delta S of the universe has to be positive. So that, this part, here's the good part. If delta G is negative, that also means that the reaction is spontaneous. So we can calculate delta G for a reaction if we know it's delta H and delta S. And as I said before, there's other ways that we can find delta G too. So we will become very familiar with how to calculate delta G and what it means for a reaction. So on the next slide, we good with this one? On the next slide, I have a very simple, I can't even call it a reaction. It's not a reaction, it's just a physical change. Solid water changing to liquid water. Do we have another name for that? It's melting. Right, it's melting. So I chose this one to start with because we all have life experience with this. We can go through this and talk about melting ice, and everybody would be kind of together and understanding all the same amount. Now, the melting of ice is endothermic. Heat must be put into the ice to get it to melt. So the value of delta H for that process is 6,033 joules per mole. Solids becoming liquids tend to increase in entropy because liquids, the particles, have more freedom of motion. So we have a positive, as expected, delta S. Now, don't let me forget. I need to talk about what those degree signs mean. How those degree signs show up. What are they? I'll tell you in a second. But let's take a look at this. This middle sentence. It presents a conflict. The delta H is not favorable because nature tends to want to get rid of some of its energy. This is taking in energy. That's not favorable for it to take in energy. However, the positive